Quiz 7 solutions for Math 243. This is our introduction to hypothesis testing. So let's see, there's a claim being made. I claim to have a drug that increases will be a keyword later on, the velocity of a pitcher's fastball. I know that the average velocity of a fastball for all pitchers is 88 miles per hour. So this is a population average, so you might think that you'd use the symbol mu here, but actually we don't. It's actually mu naught because we're going to want to save mu for something else. So in this case, mu naught equals 88. But in a random sample of 100 people, maybe 100 pitchers, whatever, the key here is that I have 100 people in my sample, therefore n is equal to 100. So 100 people on the drug, the average fastball speed, sample average, x bar, I can put that up here, is equal to 91. So the average for everybody, population average 81. The average for the 100 people in my sample taking this drug is 91. 88, I don't know if that's what I said. 91 is more than 88. The question is it enough more to conclude that the drug is making a difference? So to figure that out, we'll have to know a couple more pieces of information. One of them is the sample standard deviation. In this case, that's 12. We use the symbol S for that. S and not sigma because it's the sample standard deviation and not the population standard deviation. That also makes this a T distribution as opposed to a Z distribution. And what it wants us to do is test the claim that my drug increases fastball velocity, and then it tells us that we want 99% confidence. 99% confidence tells us that alpha is equal to 0.01. Alpha is 1%. State the null and alternative hypotheses. I don't know, alternative hypothesis, maybe that's a good place to start. It is the claim that's being made. So the claim that is being made is that my drug increases the speed of a fastball. So how do you write that mathematically? Well, we're going to let mu represent the population average if everybody in the entire world took my drug. Every pitcher maybe in the entire world took my drug. The entire population, but on my drug. Whereas mu naught is the entire population not considering the effects of the drug. My claim is that mu is greater than mu naught being 88 in this case. So what I'm saying is that if everyone in the world took my drug, the population average would be greater than what it currently is, this 88. My null hypothesis is that my drug doesn't do anything, that mu is the exact same as mu naught. In other words, mu equals 88. Because I wrote greater than right here, I know this is a right-tailed test. You don't have to write right-tailed right here, but I find it helps later on. There's the null and alternative hypotheses. Describe what a type 1 error is in the context of this problem. All right, so a type 1 error comes when you incorrectly reject the null hypothesis. So the null hypothesis is true, but you reject it. You say that it's false. So in reality, my drug doesn't do anything, but I say that my drug works. Incorrectly reject the null hypothesis. Conclude that the drug works. Maybe instead of works, I should say increases fastball velocity, but presumably you know what I'm talking about. You incorrectly reject the null hypothesis. You conclude that the drug works when in fact it does not. So a false positive is a way to think about it. All right. In order to run a hypothesis test, we essentially have to figure out a probability, and to figure out a probability, we need to know shape, center, spread. So let's see what we got here. Shape, center, spread. And I'm going to need to change this question because this has nothing to do with average vertical leap. Instead, it's average fastball velocity. You can tell I don't change my problems that much from year to year. Describe, justify, shape. Describe/justify the shape, center, and spread of the average fastball velocity. That is of our sampling distribution. The shape, it's approximately normal. It's always approximately normal in this class. It's the only distribution we know how to study. The reason it's approximately normal in this case is because my value of n is greater than or equal to 30. N, as you recall from above, is equal to 100. 100 greater than or equal to 30, central limit theorem tells me that the shape becomes approximately normal, regardless of the shape of the parent distribution. Center? Okay, let's see. Mu sub x bar. So this is the population average of all the sample averages. So I know that my sample average was 91. But that's just one of them. Like, what I want to know is what's the population average of all those averages. Well, that would be equal to mu. Unfortunately, we don't know mu, but what we do is we assume the null hypothesis is true, and the null hypothesis tells us that mu equals mu naught in this case being equal to 88. I don't know that you need all this stuff and all the equal signs. Just tell me the standard is at 88. Call it good enough. The spread, the population standard deviation of the sample averages. I'd like to use sigma over the square root of n. Unfortunately, I don't know sigma, so I'll have to estimate it using s, the sample standard deviation. S divided by the square root of n. S was given to me as 12 above, and n was given to me as 100, if I remember right. So 12 divided by the square root of 100, or if you feel like doing math in your head, that's 1.2, or maybe with the calculator. But you don't need to tell me it's this. I'm fine with you telling me it's this. Shape, center, spread. Sketch the appropriate picture for classical hypothesis testing. So we're actually going to do this problem twice. We do it once using the classical method and once using the p-value method. Later on, we're just going to be using the p-value method. But at the start, I think the classical method's a little bit more intuitive, so we'll start out by doing it that way. With the classical method, your center is 88. Let me redraw this picture so I have a little bit more room. Maybe over here. Good enough. My center is 88, but more importantly, that corresponds with a z-score of 0. And so what I got to do is I got to set up my rejection region, or regions. In this case, because it's a right-tailed test, I only have one rejection region. It's over here on the right side since it's right-tailed. And the area of that rejection region is always going to be equal to alpha. Alpha in this problem we figured out earlier was 0.01. You can see that up here. So what I got to do is I got to figure out what's called the critical value. I got to figure out the z-score, so it's going to be on the second row here, that corresponds with this cutoff point, the point so that only 0.01 is the area above this point. You're like, oh, inverse norm, I know how to do that. Yes, but inverse norm works when you have a z distribution, you have a t distribution. So you have to either use inverse t in your calculator, if you are lucky enough to have inverse t in your calculator. If you do, it'll be under second distribution. It'll be one of these. It'll say INVT. This calculator doesn't have an inverse t function, so you could either have programmed it in using a video that's up on my website, or if you don't want to do it that way, you can always go back to the t-tables. Here's a t-table that's really hard to read. That helps a little bit. My tail probability is 0.01. That's the area I have here. I got to figure out my degrees of freedom. My degrees of freedom are always 1 less than n. So since n is 100, I'm going to stay in this column here and go down until I find 99. I don't find 99. All right, I found 100 though. That's close enough. I'm going to take this value right here, 2.626, and call that close enough. Really, I want the row that says 99, but there is no 99 row. So 2.626. Make sure I got the right column there. I don't. Sorry, I want this column. See if I can keep track of that a little bit better. This value here, 2.364, it looks like. 2.364. Say that a couple more times so I remember it. 2.364. This value right here is 2.364. That's this critical value right there. Now what I got to do is I got to calculate my test statistic, and if my test statistic is in this rejection region, meaning it's greater than 2.364, I'm going to reject my null hypothesis. The way you calculate your test statistic is you hit stat, go over to tests, and do t-test. This is a t-test because this follows a t-distribution. This follows a t-distribution because we use n as a proxy for sigma. T-test says, do you have the data itself? Do you know how many miles per hour each of the 100 people threw when they took your drug? No, but I have statistics about the data. I could tell you that there were 100 people that took this drug, and that the standard deviation of those 100 was 12, and that the average of those 100 was 91, and that the average of everybody, the mu naught, was equal to 88. Those are all numbers that we got from up here. And then I come down here and I state my alternative hypothesis. My alternative hypothesis is that mu is greater than mu naught. So mu is greater than mu naught. And then I go down and calculate. Calculator, think about that for a minute. gives me some numbers. Really, the only important number here is this one, this 2.5. 2.5 is a number that's greater than 2.364. These don't have to be to scale. All that I care about is that you put this thing to the right of this thing because 2.5 is greater than 2.364. What's so important than that? Just that it's in the rejection region, that this critical value signifies the endpoint for the rejection region. So since 2.5 is greater than 2.364, and 2.364 is the boundary for the rejection region, 2.5 is in the rejection region. That's the important part. That's all. That's your picture. All right, let's draw another picture. Sketch the appropriate picture for p-value hypothesis testing. Down here we do something very similar. We, again, try our best to draw an approximately normal distribution, throw 88 in the middle, but then realize we should step down a row and really talk about the z-scores, not the actual values themselves. And here we don't have to calculate critical values. Go into those tables, we don't have to do that. All we have to do is find 2.5, somewhere way the hell out here, and calculate the probability to the right of this point, this tiny little shaded region out here. You can hardly even see it. This probability. So not this area in red, but this area in blue. This is the p-value. And in this specific case, it's equal to 0.007, approximately. The point that as we'll see when we draw our conclusion, the p-value being less than alpha, the blue area being less than the red area, means the exact same thing as the test statistic being in the critical region. Because the p-value tells me the area to the right of this little blue line right here. And alpha tells me the area to the right of this red line right here. If the area to the right of this blue line is less than the area to the right of this red line, then the blue line must be to the right of the red line. All you need to know is because, and then depending on if you're doing D or E, test stat in rejection region or p-value less than alpha. So for one of these two reasons, the first region if you were doing classical hypothesis testing, the second region if you were doing p-value hypothesis testing. For one of these two reasons, there is sufficient evidence to reject the null hypothesis and conclude that my drug increases fastball velocity. It's supposed to say increases. The null hypothesis is on trial. We just found the null hypothesis guilty, so we rejected it. The logic here is we started out by assuming it was true, that the null hypothesis was true. The drug doesn't do anything, and the center for this picture really is 88. And then we went and figured out, oh, we got a weird result. We got something that was 2.5 standard deviations above the mean. Getting a result this extreme doesn't happen very often. In fact, it would only happen 0.007 is the probability. Less than 1% of the time would you get a value this extreme. Wow, that's really unlikely. Either something crazy just happened, crazy unlikely, or maybe 88 really isn't the center. Right? Maybe the center isn't 88. Maybe the people that are taking this drug do not come from this distribution. The center, when you're taking this drug, is higher than 88. And this wasn't such an unexpected result. That's what we just concluded. All right, I guess that's the end of this quiz, so that's the end of this video.